Salam and greetings. We are Group 5, and today we are going to present our Signals and System project assignment. So I will pass to my group members to explain the first part of the task.
Hello everyone, my name is Wu Xin and the metric number is 2094.6. And today we'll introduce the passive circuit. The passive circuit is an inductive RL high-pass filter. The drawing of the circuit are as shown in the figure 3.2.1.1 below. Calculation on finding the transfer function of the circuit will let the R1 equal to R2 equal to 100 ohm, L equal to 2 mH, XL equal to J omega W, J omega L. Z2 equal to R2 times J omega L over R2 plus J omega L equal to the J omega L R2 over R2 plus J omega L. Therefore, the transfer function of the Hj omega is shown as the figure 3.2.1.4. Using the voltage divider rule, we know omega equal to Z2 over R1 plus Z2 times V1 omega. Then the V know omega over V1 omega equal to J omega L R2 over R2 plus J omega L over R1 plus J omega L R2 over R2 plus J omega. Then we get the V naught omega W over V1 omega equal to J omega L R2 over R1 plus R2 plus R1 times R2 plus R1 plus R2 times J omega L. Simply by substituting the value for each electronic component into the formula and obtaining the result frequency response as shown in the figure. Hj omega equal to V naught omega over Vi omega equal to R2 over R1 plus R2 times J omega over J omega plus WC. WC equal to the 100 times 100 over 100 plus 100 times 2 times 10 to the power of -3 radian per second. Then we get WC equal to 12.5 K radian per second. Apply KVL with the Laplace transform in the next one. When Vi is equal to R1 plus R1 times I1S plus LS times I1S minus I2S. V1 equal to R1 plus LS times I1S minus LS times I2S. Apply KUL with the Laplace transform LS times I1S plus R2I times I2S equal to LS plus I1S. We get the I1S equal to R2 plus LS over LS times I2S. Substitute the equation number 2 and into the equation number 1, we got the I1S equal to I1S equal to R1 plus LS times R2 plus LS over LS times I2S. Then we got V naught S equal to R2 times I2S. Then when get the transfer function GS equal to the V naught S over Vi is, then we got R2 over I1 plus L2 LS times R2 plus LS over LS minus LS. Then we got GS equal to the 0.2S over 0.4S times 10K. Here is the high pass filter circuit multi-zone simulation. Then we got the result of the high pass filter multi-zone signal. At last, we're using the MATLAB to do the simulation. And from the figure 3.2.1.8, the input step of the system of the output is following a decreasing trend. When the time goes up, the amplitude will decrease.
So to recap, the part B of the first passive filter. So we decided to go with the low pass filter, and this is the circuit that we chose. We decided to go for something easy so that we can calculate manually in without having difficulties, and also able to simulate it in MATLAB and also the multi-sim. And as for the value inside here, we decided to go with these specific values. So we have already written there the resistors and also the inductors value. It's not too high because that if it's too high, it will be harder for us to get the output or to get the exact value that we wanted. So we decided to go for something low so that it will be it makes our process easier and also ease and smoothly. So for the transfer function, we decided to use Laplace transform. So from what we can see here, that from what my team explained, the XL is equal to J omega L. As what have he explained. So we've gone through the Laplace transform, and from the Laplace transform from this figure here, you will get the transfer function. However, this is without the value, and this is just to find the exact formulas or to find the exact output response throughout using the theoretical method. So for this part, decided to simulate it in multisim. And if you can see here, there's a multimeter. The function of the multimeter is to see whether or not there are output response from the circuit. Because if there's no output, then you will not be able to get the signal. And we decided to use oscilloscope to generate the graph itself. So this is the graph that we get, and also meaning that the circuit works. So even though the value is quite small, but it's not very complex, so the circuits is very able to be conducted and able to get the excitations and also the output response. So this is a very good way to identify that we can proceed to get the MATLAB simulation. As for the MATLAB simulations, we use the calculation method to find the response of the MATLAB. However, before we proceed with the MATLAB simulation, um, in our report, they are actually another calculation that will be included, which is the it's called figure 3.2.1.4. I'm so sorry for the trouble. It's not included in slide. For the figure 3.2.1.4 in our report, we did another calculation. We did another calculation. This is to verify the transfer function that we did manually. So from that, we'll be able to obtain the exact output response. So we put in the values that we chose in the manual. So this is the simulation of the MATLAB that we get from the MATLAB simulation. So this is how we get. And as for my presentation, I will present my active filter, which is the Butterworth filter, or also known as low pass filter, if we did a lot of research. So decided we would like to study this case, and we followed one of the examples online that we get. And what intrigues us is that this is very complex and so interesting for us to study and to make analytical analysis to find the transfer function in signal and system. So we use a pre-made value where the resistors and the inductors are it's already here. And inside this circuit, they use the OPM components. And this one is the non-complex component. So it's just a very straightforward components instead of having multiple legs. Some of the OPM has different has some of them have multiple input and outputs. So, but we're not going to use more complex than that, but we use this simple ones in the circuit. And however, the overall circuit is a bit complex, it's a bit tricky because there are additional few components before the input and also at the connection of the circuit itself. So we decided to go for the circuit because of the complexity, and we like to challenge ourselves to find the transfer function. So for this part, we use the Laplace transform to find and simulate the uh, output response. So this is the first manual calculation that we did. So we, of course, we use the Laplace transform of the circuit. So what we did is that we hold on. Uh, okay, okay. So all right. So we put in we study the circuit. First, you have to analyze and study circuit. Before you put down the manual calculation, you need to understand how does the path of the circuit works from the current and also the knots and also the mesh. So from there you study and then you bring out the exact not cover formulation of the circuit itself. From there, you will expand and use the Laplace transform theoretically and apply in the values to find the output response. So throughout that particular calculation, so from here you can see that the VO over VI, this is the output response, is actually 1000 divided by s to the power 2 plus 150 s plus 1000. Right. So this one is to so you get the output response. Of course, you can also find the cutoff frequency. This is an additional uh, findings towards our calculation. You can able from the output response you can get the cutoff frequencies. As for the simulation, so this is the simulation that we did in multisim. Um, this one is a bit tricky because it takes several attempts to get the output or to get the output response of the simulation. We changes the power supply and we try to change the component value, and somehow this is one of the not the best due to time constraint, not the best, but this is one of the a good finding that we're able to get and to do research on. Um, from the simulation, of course, we use both oscilloscope and also the plotter. Now, the problem with the oscilloscope that we don't get the signal that we wanted, and that's somehow there's a problem. From here, you can see that the output itself is at negative value, so which means that the value is actually very, very low of the output response is very, very low. We're still trying to find out what's the problem. It's maybe because of the low power supply, and also a very high value of component because we use 10Ks and 20Ks of resistors, which reduces the amount of currents very, very high. Um, Maybe there's a possibility because we actually try to find ways to conduct that. However, um, we use bot bot plotter to get the circuit. So from here, you can see there's a signal. Okay. Um, from what we can understand here is that there are times where there are cases in Butterworth filters, bot plotter is a better option to be used to check on the signals of the output response rather than the oscilloscope. I mean, there oscilloscope can be done, but it requires a more in-depth learning or in-depth understanding towards the component. So from the bot plotter, okay, we can understand that it is that the output actually coincides the representation of the frequency response. So it shows that the filter do effects on different frequencies and how it maintains a consistent gain across the passband. So in this case, so the bot plots are preferred for analyzing and also to provide a comprehensive visualization of the filter frequencies response characteristics. So that's why. In terms of MATLABs, we're having problems with getting the output response somehow. We try multiple runs, but we having technical issues and the error. But due to time constraint, we are trying our best to uh, to get the MATLAB. However, we also provide another methods using another manual calculation to support our evidence, to support the findings that we get. So in this circuit, in this manual calculation, we decided to transform the time domain into the S domain using the Laplace transform. So this is another way or another approach to support the calculations. So from previously the first calculation, that is our first method. So this is the second method. So from the second method, of course, we apply the KCL value to the Laplace transform, and of course, from the beginning, you have to obtain the circuit flow of the for the formulation before you conduct the KCL, and also you need to apply the meshes and also the nodes in the circuit. So you have to understand. So this is the tricky part when you perform a MATLAB because of the complexity of the circuit. You need to understand clearly and deeper in these findings. So in terms of that, this is the manual calculation that we managed to come up with based on the value. And you can see that the output response, it is 1000 divided by s to the power of 2 plus 140s minus 500. So this is our output based on this one. However, we did a little bit of changes in the capacitor. So usually for the previous manual equation, we just straight direct. However, this will be transformed the 5 micro and also the 1 micro into 1 over the value, and also another 1 over of the value. This provide a different insight. This provide a different insights of the output response. So from what we can learn is that um, the the calculations actually prove that this is a low pass filter because it stops the frequency that are greater than the cutoff frequencies and of the filter, and also it amplifies the frequency below the cutoff frequency. So we have this manual calculation to support our evidence towards the circuits, rather despite of not having a MATLAB simulation, which I truly apologize for the trivial matters. Um, Yes. I think that's all for our presentation. Thank you so much.